In this video, we're going to be starting to talk about line integrals. And more specifically, we're going to just be referring to scalar functions. So, what do I mean by that? What is a scalar function? A scalar function is just your traditional function that everyone is used to. So, f of xy is equal to, I don't know, x squared plus y squared. This is a scalar function. It has a scalar output and has scalar inputs. The other type of line integral is integrating vector fields, but that's not what we're going to talk about today. We're just going to talk about typical functions that have outputs of scalar values, or standard algebraic functions, or maybe graphable functions that we have here. So, what is a scalar line integral? So, the general formula for a scalar line integral is just the integral with some bounds of your function f of xy of your, I guess, infinitesimally small line differential. So, maybe I said that wrong. I don't know. But ds just stands for some infinitesimally small line, I guess. So, whenever you have a line integral, you're going to have some parameterization of, I guess, a line on the xy plane, and you're going to have some function in 3D. So this is a function in 3D, correct? If your function was x squared plus y squared, you would have a paraboloid. And you're going to have some parameterization. Maybe it'll tell you your parameterization is a point from 0, 0 to 1, 1 on the xy plane. And once you have that parameterization, you can actually expand your formula like so. So when you have a parameterization, your x and your y values are going to be a function of some new variable, t. And you would want to find the, and let me be more specific with this, this is ds, and you would want to find the arc length of your curve, which is just the integral of your derivative of the magnitude of your parameterization. So this is just going to be the general. This right here is the very, very general formula, and this right here is more of a actually usable formula. And I'm going to show you what a scalar line integral looks like on Desmos right now. So we have an example here of what a scalar line integral could look like. And let's show you with the classical canonical x squared plus y squared, one of the most simplest forms you can write a paraboloid in. So you have some parameterization. In this example, it's a sine function along the xy plane. And you can solve for the area between your function, paraboloid in this case, and your parameterization. And when you mark that out, it actually looks like this. So this is just a 2D surface. It's completely flat. And it's simply the area under your surface, so to say. And when you solve for the line integral, you solve for some, let's see, we can limit your blue part of x as, I don't know, like this, like so. So this is just from x 0 to 2. And you can actually find the area of this surface by solving for the line integral using the general formula I gave you previously. That's enough talking though, because showing you actually how to do the problems is way better than just explaining general formulas or the like. I remember when I was in lecture and I was first learning these, it absolutely did not help at all if we didn't do example problems in class. I think actually doing example problems would be very helpful. This doesn't really tell much until you actually do the problem. So, as I explained before, r of t is your parameterization. And if I just show you the general formula, you have no idea how to find a parameterization. I think practice to solving the general formula will help you a lot. So for this problem, we have our function here, and we have, I keep clicking Control X, we have our parameterization here. And this is simply just a straight line. I should put that information, but I thought I would just say it. Try to solve for this if you, I guess, already have some knowledge about it, using this general formula about how to solve scalar line integrals. So assuming that you've tried, or at least attempted the problem, I'm going to show you how to solve this. So first thing I'm going to do is find some parameterization. So if R of t is just, I guess, you can describe it as a vector. And the reason why I'm setting this as a parameterization is because our bounds for t will be from 0 to 1. So when you plug in 0 here, you get, let's change the color, you get 0, 0 as the output, correct? And if you plug in 1, 1 here, you get 1, 2. And anywhere in between, like 0.5, you would get some linear function, a straight line, so to say, from 0, 0, 0 to 1, 2. And that is our goal for this. Because now that we have our bounds, 0 and 1 for t, that would be the bounds for our integral. Right here in your general formula. So, next thing you'd want to do is find your derivative of your parameterization. And then you'd want to find the magnitude of your parameterization. So the derivative of your parameterization is just 1 and 2. And the magnitude of your parameterization is the square root of all values inside of your vector squared, or all values inside of your parameterization squared. So this 1 squared plus 2 squared square root is equal to the square root of 5. That is simply just this element here. So if you remember this general formula, you'll be able to solve for the entire thing. It's going to be pretty easy. It tells you all the steps that you need to do. And ignore the ds. If you just remember this entire thing, honestly, that other general formula that I wrote before is just completely useless. Doesn't actually tell you how to solve the line integral, but it tells you how to expand it, I guess, into this form, which is the actual practical form. So now that we have our, let's write this in green because it's important. Now that we have our magnitude of your parameterization, you can write down your integral parameterize. So x is a function of t, and right now this is your function of x, and this is your function of y. Correct? This is the x component of your parameterization, this is the y component of your parameterization. And if you substitute t into here, into your x value, you get t squared. And if you substitute 2t into your y value, you get 4t squared. And don't forget, you have to multiply all this by your magnitude of your parameterization and dt. So our bounds, remember for t, are 0 to 1. There you go. The bounds that we found in our parameterization for the straight line from this point to this point is our bounds for our integral. So 0 to 1 here makes sense because when you plug in 0 into r, you get 0, 0. When you plug in 1 and 1 into r, you get 1, 2. Simply a straight line. So all this is now is just a calculus 1 problem. It's a single integral that you can easily solve. Actually, you know what? Let me not do that so I can have a thumbnail. Let's just keep writing. So if you want to solve for the integral of this, you can factor out the square root of 5 of your integral. It's simply a coefficient. And you can simplify your t squared plus 4t squared as 5t squared dt. And if you solve for the integral of this, you get Let's write this in angled brackets. Close. This is 5 over 3 t to the power of 3. And your bounds are 0 to 1. So if you just plug in 1 here, you get 5 square root of 5 over 3. Plug in 0, you get nothing. So this is our answer for the first problem. This next problem is slightly different. Now your parameterization is a parabola. It is not a straight line. So you're going to have to do something a little bit different in order to be able to write down your parameterization. So as always, the first thing that I do is find your parameterization, R of t. And the parameterization for this is, actually try this problem out first before I tell you the answer. There you go. Hopefully you paused it. But the parameterization for this is t and t squared. So remember, this is a function of x, and this is your function of y. And if you were to plug in 0, 0, 0, 0 into t, your outputs for this would be 0, 0. And my intention was of this was to make, again, your bounds for t something simple, like 0 and 1. Usually you would like to make your bounds from 0 to 1 if possible. If not possible, then you could just simply, what am I doing? If not possible, you can just simply make your bounds something else, like 0 or 1. I mean 0 or 2, sorry. Let's underline this to keep in mind these are our bounds. If you plug in 1, 1, you'd get, again, 1, 1. But the path is different. If you plug in 0.5 and 0.5 into this formula, you get something different than the previous one. The previous parameterization was a linear function. But now we have an exponential function that has a t squared. Not exponential function, sorry, like a parabolic function, more like. Exponential is like, I don't know, e to the power of x. And also, quick thing, this parabola is represented by x squared is equal to y. So if we just parameterize our x value into here and our y value into here, you get t is equal to x. So you get t squared. And y is equal to t squared, so you get t squared. So our parameterization makes sense in terms of this parabola given. Let's erase those arrows. Now that we have a parameterization, I find the derivative of our parameterization next. So the derivative of t is 1, and the derivative of t squared via the power rule is 2t. And our magnitude is all the values squared, square rooted. So our magnitude is 1 squared plus 4t squared. And that's just equal to 1 plus 4t squared. So this is our magnitude. Looks a little bit weird, but we can still solve the problem in this case. And let's go box this up in like green or something. Let's write it with green actually, like last time. 1 plus 4t squared. So what do we do next? Well, we have to parameterize our function in terms of t. So x is equal to t, y is equal to t squared. We can substitute all our values in. If there was a y value here, we would substitute with t squared, but since it's just an x value, our integrand is just t times the magnitude of your parameterization. The magnitude of the derivative of your parameterization, which is this, dt. And your bounds are 0 to 1 because it makes sense within your parameterization and your bounds here. So all we have to do is just solve for this integral. And for this, you need to use u substitution. So let's use u substitution. I'm going to choose, I don't know, 1 plus, I'm going to choose whatever inside the square root as our u substitution. We'll substitute as u. And we need to solve for du is equal to 8t dt. And then du over 8t is equal to dt. So we can actually substitute dt in as du over dt. So if we were to do that, you'd get t times 1 plus 4t squared times du over 8t. And don't forget to change your bounds. If we were to plug in 0 into this t value here, you'd get 1 as your u value. So your lower bound for your new u substituted integral is 1, because I plugged in 0 into your function of u. And we just plug in 1 into t here. If we plug in 1 to t, it's just 1 plus 4. So that's 5. So your new upper bound is 5. These cancel out, and you get left off with another integral, like so. 1/8, 1 to 5, square root of u technically, du. And this u just came from our u sub. U is equal to 1 plus 4t squared, so I can just substitute 1 plus 4t squared as u. And all that we do is solve for this integral. So the integral of u to the power of 1/2, which is just u square root, is 2 over 3u times 2, 3 over 2. And our bounds are 1 and 5. And in the end, all that just equals to, my notes will tell me. All that is just equal to, 5 square root of 5 minus 1 over 12. So this right here is the answer to your line integral of this with our parameterization given by a parabola. Now, for this problem, you're going to have to use, I guess, a good old friend of yours, polar coordinates. Polar coordinates, kind of, because your parameterization is now a circle with radius 2 in the first quadrant. So, how would I parameterize this first, after you guys do the problem? I would parameterize this using kind of a concept that you learned in polar coordinates. So in polar coordinates, x is equal to r cosine theta, right? And y is equal to r sine theta. But here's the thing about this. We have our radius. Our radius is 2. So r is equal to 2 here. So what can we do? Well, in the parameterization, your x component is your first component, and your y component is your second component. So our parameterization for x can be 2 cosine theta. Because the radius is 2, we can substitute r as 2, and cosine theta stays as our value. I guess you can change that as t, because this is a function of t. So this is 2 cosine t, and your y value would be 2 sine t. And since our circle is in the first quadrant, the bounds for t are just from 0 t to 2. Sorry, pi over 2. I almost instinctively wrote 2 pi, because that's the bounds for a full circle. But 0 to pi over 2 is simply from here. This is the value of 0. Sorry, this is like a value of 0, and this is on the positive y-axis is the value of pi over 2 in radians, which makes sense because we are just staying within the first quadrant. So now that we have our parameterization, let's find the derivative of this. The derivative of r of t is negative 2 cosine t. 2 cosine t. And our magnitude of our parameterization is magnitude of the derivative of our parameterization is square root of 2 sine t squared plus 2 cosine t squared. And all this just simplifies to 2. So let's keep drawing in green. Let's keep this safe and sound for now. But let's set up our integral. So our integral will be set up with bounds 0 and pi over 2, as we discussed before. And our new parameterization is simply just y. So our function f of x of y is just dependent on y. So all we have to do is just substitute in for y. Now, don't make this mistake, because sometimes when I was solving these problems, I would substitute in my derivative in. So this is the y component of my derivative. I would substitute that in for y, which isn't right. You want to use your just r of t, not r prime of t. So for y, it's 2 sine of t times your magnitude of your derivative of your parameterization, which is just safe and sound, in green over here, which is 2. So we can leave that out since it's a factor. Actually, let's be a little more consistent than that. Let's leave it in front. Now that we have this, again, this integral is just a Calc 1 problem. Right? You could probably solve this in Calc 1. I'd hope you could. If you can't, then go talk to your teacher. But this is just a Calculus 1 problem. And like so, you can just solve it like a Calculus 1 problem. So we can factor out the 4, and all we're left off with is 0 pi over 2 as our bounds, and we have sine of t dt inside of our integral. So sine of t is our integrand. The derivative of that is just negative 4 cosine of t, and our bounds are 0 and pi over 2. So if we plug in pi over 2 into cosine, you get 0. Minus, if you plug in 0 into cosine, you get 1. So 1 times negative 4 is just negative 4. Therefore, our answer is 4. So, as always, if you have any questions, put it down in the comment section. Have a great summer, or if you're studying to go back to school, which I know some of you are, good luck with that.